Hello everyone and welcome back to the another class of fundamentals of particle and fluid solid processing. We will continue our discussion on the centrifugal separation. We started in the last class the discussion on its working principle, on the introduction, and we have seen this part, that is the efficiency and separation. So, we will quickly go through this part once again in order to maintain the coherency. So, say the solid mass flow in the cyclone is m, the solid's mass that is discharged from the outlet, which is mc, c stands for the coarse particle. So, that is actually the particles that we are separating, and the other flow rate, that is the solid's mass flow rate with the cleaner gas, this is basically a finer particles that escape with the clean gas. And since the cyclone efficiency is not 100%, although theoretically it can be, so these are the impurities that goes with the clean gas. Now, if we do the total solids material balance, we can write this expression that m, which is the total mass flow rate of the solids, is equals to the mass that is being discharged, or the solids that is being discharged from the coarse outlet and the finer outlet. And if we do the component material balance for each particle size of x, then we write that m multiplied by the size distribution of the inlet, that is this f df d by dx of f is the differential frequency size distributions of the solid particles for the inlet or the flow rate that is coming in the cyclone separator. Similarly, ddx by ddx of f stands for the finer particle. So, this is the differential size distributions of the solids in the finer particle collection, or say the clean gas collection outlet, and accordingly this dfc by dx is basically the differential size distribution frequency by mass of the coarser particles. Now, we know the relation between the differential size distribution and the cumulative size distribution. So, this f and fc, this small f and small c, these are the subscripts for the finer and the coarser particles. These are the cumulative frequency size distributions by mass. And then the total efficiency by definition becomes the mass fraction of the coarser particle or the coarse particles that is collected from this operation, which is mc by m, and the grade efficiency is the mass of solid of size x in the coarse product divided by the mass of solids of size x in the feed. So, grade efficiency, as I told last time, it is of a certain particle size. The example that I gave, say you want the suspension or say the particle laden gas to be free from say certain particle size, that is your x in this expression. Say you want that particle laden gas to be free from size of particles of more than 15 micron. So, this is the size, that is x is 15 micron in this case. So, 15 micron of particle in the coarse product divided by the 15 microns of the particle in the inlet or in the feed. This ratio is the grade efficiency of that cyclone separator. So, by this definition, grade efficiency can also be written in this form. This is the mass of solids multiplied by the size distribution of size x in the coarse product divided by the mass of the solids in the feed multiplied by its size distribution. And again we know this MC by M is basically the overall efficiency or the total efficiency of the cyclone separator. So, which means we can write the grid efficiency in terms of total efficiency as well. Now, these three expressions, that is this overall efficiency, total expression and this component material balance, this yields to this expression, which is the size distribution of the particles in the feed, in the coarse product and in the cleaner gas with the fine particles related with the overall efficiency. If we integrate this, we get this cumulative mass fraction or size distribution based on the mass. So, this was the point we ended or I ended the last class. So, basically this expression or these two expressions are of importance because these two expressions give us the product size distributions or say the particle size distributions from the feed, in the coarse and in the finer particle, in the clean gas outlet. So, if we know these two, we can calculate the third one with the help of its total efficiency. We will see example related to that how these expressions are utilized in some problem. Before that, let us look into the flow pattern inside this gas cyclone. Now, as I mentioned last time, as its working principle, this particle and the gas stream or the particle laden gas stream are forced into a circular motion inside the cyclone by introducing it tangentially with a very high velocity. So, it creates vortex inside that, and once it comes down in the conical section, it changes its direction and the clean gas goes at the top, because the particles, this free vortex moves the particles towards the radial directions and it hits the wall, and due to the gravity it moves down and is collected at the bottom of the cyclone. So, basically what happens, this net gas flow is basically radially inward, and the forces that are acting on the particles are the drag, buoyancy and the centrifugal force. Now, the direction of drag force, if you realize here, the particles are being pushed towards the wall, the gas is inward. Okay. So, the relative velocity based on the particle is basically outward, because it has to be captured. So, that velocity is higher, and that means the drag force is basically inwards, because it is opposite to the direction of relative velocity. So, the drag force F d is inward. So, here this picture shows that based on the balance of these forces on a particle, if it comes to a balanced expression or the forces are balanced, then it assumes a certain orbit of say radius small r. So, a particle size x of density rho p has attained orbit of radius r, and it is moving in that radius of orbit. Also assume the gas density as rho f and viscosity is mu. Say the tangential velocity of the particle is u theta. Okay. This is the u theta, and the radial velocity is u r. This is the view from the top, and this is the particle motion. the particle trajectory. So, say the radius of this cylindrical portion is r, the length till this position is capital L, okay, and this is the velocity inlet. If you look from the top, this would be the velocity inlet, this is the gas outlet, this is the radius of the cylindrical section. U theta is the tangential velocity. So, U theta r is the tangential velocity at the wall, and U capital R is the radial velocity of the particle, say on the wall of this vessel. So, if we assume, say for the time being, it is not touching the wall, but having a trajectory or orbit of radius small r, that is the diameter x of the particle, density is rho p, and the orbit of radius r. Tangential velocity u theta and u small r. So, the drag force, and if you assume, say all this operation is happening in the Stokes law region, then the drag force acting on the particle is this expression that we know already, which is Fd is 3 pi x mu u r. So, this scenario, the particle on equilibrium orbit of radius r, when these forces are in equilibrium, that is the drag force, buoyancy force and centrifugal force. So, out of which Fd is 3 pi x mu r. Then this centrifugal force, which is Fc, okay, we can write this expression, that is pi x cube by 6 rho p u theta square by r, where u theta is the tangential velocity of the particle, that is having a trajectory, that is moving in an orbit of radius r on equilibrium. Similarly, the buoyancy force we can write Fb is equals to pi x cube by 6 rho f, here is the density of the fluid, u theta square by r, and at equilibrium, based on the direction of the forces, as I mentioned that Fd and Fb is inward and centrifugal force is acting outward, which means Fc is equals to Fd plus Fb. C stands for the centrifugal force, D stands for the drag force, B stands for the buoyancy. If we equate, or if you now replace these expressions of Fc, Fd and Fb, you would achieve an expression of particle diameter with this parameter, that is 18 mu divided by rho p minus rho f multiplied by r divided by u theta square multiplied by u r. So, 18 mu divided by the density difference of the particle and the fluid, r is the radius of the orbit that a particle of dimension or diameter x has taken at equilibrium, u theta is the tangential velocity, u r is the radial velocity of the particle. So, we find an expression of the particle diameter and its equilibrium radius, radius of the orbit. So, now the point is that before we proceed any further, we need a relation of this u theta or expression for u theta, because it is the u theta at an arbitrary position having a orbit of radius small r, which hardly can be measured. So, u theta, now for a rotating solid body, u theta, the tangential velocity, is the orbit radius multiplied by the angular velocity, this we know. And for free vortex, u theta r is constant. And when this vortex is confined, it has been seen experimentally and has been observed that u theta r to the power 0.5 is constant. This is experimentally determined or experimentally observed for confined vortex, that the tangential velocity and the radius of orbit to the power half or 0.5, this is constant. So, which means this u theta small r to the power 0.5 is basically equals to u theta r, the solid say touching the wall, multiplied by the radius of the cylindrical section, because the particles basically touches this wall and then falls. When it impacts on the solid wall, then it is being collected by gravity, it rolls down at the bottom. So, now that means we have an expression for u theta in some known quantity, because u theta r is basically a design parameter. It comes from the design of this cylindrical section and the operating condition, as well as r is known from the design parameter, the capital R. So, now if we assume that the uniform flow of gas towards the central outlet is there, an ideal scenario, then the gas flow rate at every plane remains same, because that is the net flow rate that is happening at every plane. So, which means if the gas flow rate Q is basically known, then 2 pi r small r multiplied by L multiplied by u small r. This is the volumetric flow rate at this plane of radius small r, which is equals to 2 pi capital R capital L multiplied by the radial velocity at the wall, the particle that is touching the wall at that position. So, which means we find a relation of u small r with u capital R. Now, here u capital R again is a design parameter, because this tangential velocity and radial velocity, these are the design parameters of this gas cyclone at the inlet near the wall. So, whatever happening at an arbitrary small r position, we have now found the expressions relating to that position with some known quantities. We did that with u theta r, theta r means near the wall or at the wall, and u small r in terms of u's capital R. So, these two expressions here, because in this form these were the two unknowns basically, u theta and u small r, that we derived by the equilibrium force balance. Now, we replace these two, that u small r in terms of u capital R and u theta in terms of u theta r in this expression. We get x and the relation of small r in terms of all known quantity. Now the point is that this small r is still the radius of orbit where a particle of diameter x has attained at equilibrium condition, equilibrium between the three forces of drag, buoyancy and the centrifugal force. Now in order to be this size of x be captured or to have in the course product outlet, this particle has to collide with the, or it has to come to the surface of this vessel. That means this orbit of its movement, this small r has to be the capital R, and then it can basically touches the wall and can be captured. So that is the critical x, the radius of this equilibrium orbit when it becomes the radius of the vessel. That means it hits that wall or it touches the wall, and then once it touches, that means that particle can be collected. So replacing that small r with the capital R, we can find the critical diameter of the particle that can be captured, and that comes in terms of particle density, fluid density, fluid viscosity, the particle radial velocity and tangential velocity near the surface or say near the wall. So this critical size is sometimes a single quantity that is used to quantify a gas cyclone. The characteristics of a cyclone separator is sometimes quantified by this critical particle size that can be captured for this operating condition. So I hope this expression is clear to you, that how this critical particle diameter can be calculated provided all other design parameters are given. Now, which means if this is the case, the grade efficiency for say this x size or x critical would vary very sharply, ideally, that there will be a sharp line that beyond this line everything will be captured, or beyond this size everything will be captured, and these particles will escape with the finer k. But that does not happen. This simple theory that we have shown, this should predict that this is your x critical and this is the critical size that can be captured, or higher than that, larger size than that, and any smaller size than critical size will basically still be in rotation, and the chances are that it will not be captured because it is not touching the wall. So ideally this is the case, but the point is that in actual practice it has been seen that even though there is a x critical, few particles smaller than that gets away or collected, or say higher than that is escaping, and this happens due to gas velocity fluctuations, particle particle interactions. These two are the reason, the point why we do not get this kind of ideal or 100% separation with a critical size. So, this measurement of efficiency, the particle size at grade efficiency 50% or say x 50 is the number. Sometimes these are used for characterizing a gas cyclone operator or its efficiency. So, why this 50%? X 50, the particle size at grade efficiency of 50%, because this is a equiprobable number that 50% chances are there the particles of this size will be collected, of this x 50 size, the critical size. That does mean that for larger quantities of particle, 50% of the particle that is higher than this size will be collected as the coarse product. So, this x 50 is also called as the cut size of the cyclone. Now, this parameter is very useful as a single number in scale up operations or scale up calculations from a laboratory stage to the commercial scale, because this cut size is independent of feed size distribution. So, that is the reason that this cut size is one of the vital parameter that is used for the calculation of scale up designs. So, what does that mean? That whatever we have covered now is that we have seen the flow pattern, or we have seen that how a critical size of a particle that can be captured for a given operating condition can be calculated or determined. We have also understood that that ideal scenario is not practical, is not feasible, and the grade efficiency of a cyclone typically takes a shape of this kind of a S shape of curve, like the other separator that handles this this centrifugal force and the drag force balance. There is a single number we have tried to identify, which is called the x 50, that is the grade efficiency at 50%. So, this value we say is the cut size of the cyclone, because this gives a possibility of 50% chances that the size of this will be collected in the coarse product, and this x 50 is basically independent of feed size distributions, and that is why it is useful in scale up calculations. So, with this I will stop here today, and in the next class we will be dealing with couple of problems related to this grade efficiency, overall efficiency, how the size distributions can be calculated if these two values, if the two outlet values are given, and we will see the range of operation of these cyclone separators. Till then, I thank you for your attention.